Somewhere around 5,000 years ago, a merchant in ancient Mesopotamia sat beside a pile of grain sacks trying to remember who owed him what. Not philosophy, not mathematics, just grain. Maybe one farmer had borrowed 6 bags during a drought and promised to repay 8 after the harvest. Maybe another trader had already paid half his debt, but not the rest. Maybe a shipment arriving from another city was delayed because the river current had turned violent again. And the problem was not greed. The problem was memory. Because human memory is strange. It is emotional, selective, fragile. It forgets numbers. It confuses dates. It quietly changes details over time without asking permission first. And that becomes dangerous the moment a civilization grows larger than a single village. One person can remember a few transactions. A kingdom cannot. Sometime around 3000 BCE, people in Sumer started pressing markings into wet clay tablets, tiny symbols representing grain amounts, livestock, taxes, debts, land ownership. Information that could now exist outside the human brain. At first, these records were painfully simple. Who paid? Who owed? But something profound had happened. Humanity had invented external memory. Not computers, not databases in the modern sense, but the core idea underneath every database that would ever exist had already appeared. Information could now survive independently of the person who created it. And once civilizations discovered that, everything began to change. Because civilizations do not run on stone or gold or armies. They run on information. Who owns land? Who owes taxes? How much food remains for winter? How many soldiers are available? Which laws apply to which people? Without reliable records, large societies collapse into confusion astonishingly fast. The Egyptians understood this. The Roman Empire understood this. Ancient Chinese dynasties understood this. The larger a civilization became, the more desperately it needed systems for storing information accurately. Not because humans became smarter, because humans stayed forgetful, and forgetfulness scales badly. A village can survive rumors and missing paperwork. An empire cannot. Imagine trying to run a kingdom of millions while relying entirely on human memory. A tax collector forgets one shipment. A census official miscounts one district. A merchant disputes a debt from 3 years ago. A military officer loses records about food supplies before winter. Tiny mistakes begin multiplying through the system like cracks in ice. This is why ancient civilizations became obsessed with records. Entire classes of scribes emerged whose full-time job was simply maintaining information. In some cities, record keeping became one of the most respected professions in society because information had become infrastructure. Not physical infrastructure, cognitive infrastructure, the memory system of civilization itself. And memory has always been expensive. Clay tablets took labor. Papyrus took labor. Libraries took labor. Archiving took labor. Even ancient history is partially shaped by which civilizations managed to preserve their records long enough to outlive themselves. The famous Library of Alexandria was not important merely because it contained books. It represented something much bigger, the realization that knowledge itself could be centralized, organized, protected, and retrieved later. That human understanding did not need to disappear every generation. That information could accumulate. For most of human history, forgetting was normal. Knowledge vanished constantly. A farmer died without passing on a technique. A mathematician's notes burned in a fire. A ruler erased records of political enemies. Entire libraries disappeared during invasions and wars, and every time it happened, civilization lost pieces of its memory. This is one of the strangest things about human beings. Our species became dominant, not because individual humans are extraordinarily powerful, but because we learned how to store and transfer information across time. Language did part of that. Writing accelerated it. But record systems changed everything, because the moment information becomes searchable and organized, civilization gains continuity. The future can build on the past instead of constantly restarting from zero, and this created a new problem almost immediately. The more information society stored, the harder it became to manage. A few clay tablets are manageable. A room full of tax records is difficult. An empire generating millions of records becomes something else entirely. Now, memory itself starts becoming overwhelming. Imagine standing inside a massive Roman archive filled wall to wall with records, land records, trade records, military inventories, legal disputes, population counts, ship manifests, tax payments, everything written by hand, everything organized manually, everything vulnerable to human error. One misplaced document could create chaos years later. One mislabeled record could trigger legal disputes no one could untangle, and unlike modern systems, there was no search bar, no instant retrieval. Finding information often meant physically searching through enormous collections by hand. Civilization had solved one problem only to create another. Human beings could now preserve information, but they still struggled to navigate it, and that tension never really disappeared. In fact, the entire history of databases is basically the story of humanity trying to solve one increasingly terrifying question. How do you organize memory at civilization scale? Because as centuries passed, information kept growing faster than human beings could manage it. More trade, more people, more laws, more transactions, more records, more complexity, and eventually paper and human memory would no longer be enough. Human civilization was heading toward an information explosion. It just had not realized it yet. The first databases did not glow. They did not hum with electricity. They did not exist inside machines. They sat in dusty rooms under torchlight, carved into clay by exhausted human hands. And for thousands of years, that was enough. In ancient Sumer, scribes pressed wedge-shaped symbols into wet clay tablets using sharpened reeds. The symbols represented livestock, grain shipments, property transfers, taxes, labor obligations. At first glance, they looked primitive, broken fragments of a distant world. But those tablets were doing something astonishingly modern. They were structuring information. This tablet belongs to this merchant. This grain shipment arrived on this date. This debt remains unpaid. Rows, categories, ownership, transactions. The underlying logic of databases already existed long before electricity did. And once civilizations discovered organized information systems, they started scaling in ways that would have been impossible otherwise. Because power does not scale through strength alone, it scales through coordination. And coordination requires records. The Egyptians understood this deeply. The civilization surrounding the Nile River depended on cycles that had to be predicted and managed carefully. Flood seasons determined agriculture. Agriculture determined food supply. Food supply determined political stability, which meant information became survival. Ancient Egyptian administrators maintained enormous archives recording harvest yields, tax payments, land ownership boundaries, construction logistics, census counts, and labor assignments. Temples became administrative centers partly because they already possessed literate scribes capable of maintaining records reliably. And reliability mattered. If grain storage records were inaccurate, entire regions could starve during drought years. If tax records failed, military funding collapsed. If land ownership became disputed, political instability spread quickly. The empire functioned because information flowed through it continuously. Not unlike a nervous system, this pattern kept repeating across history. As civilizations became larger, their information systems became more sophisticated. Then came the Romans, and the Romans turned bureaucracy into an empire-scale machine. Rome is often remembered through soldiers and architecture and conquest. But underneath all of that sat something quieter and arguably more important: administration. The Roman census system was one of the most powerful organizational tools of the ancient world. Officials tracked populations, wealth, military eligibility, land ownership, and taxation across enormous territories stretching over 3 continents. Think about the scale of that for a moment. No computers, no printing presses, no telecommunications. Yet somehow the empire maintained records across millions of people because Rome understood something fundamental. An empire is only as strong as its ability to process information. A governor cannot govern territory he cannot measure. A military cannot feed soldiers without inventories. A taxation system cannot function without records. And once again, information became infrastructure. Storing information creates another challenge almost immediately. Retrieval. A record is useless if nobody can find it later. This is where archives and libraries became revolutionary, and no ancient institution symbolizes that more than the Library of Alexandria. The Library of Alexandria is often described romantically as a collection of books, but in practice, it was something far more ambitious. It was an attempt to centralize human knowledge itself. Scholars gathered texts from across the known world: mathematics, astronomy, philosophy, engineering, medicine, geography, literature. Information from different civilizations suddenly existed in one organized system. That mattered enormously because when knowledge becomes centralized, ideas begin colliding with each other. Mathematics influences astronomy. Astronomy influences navigation. Navigation influences trade. Trade influences wealth. Wealth funds more scholarship. Information systems do not just preserve civilizations, they accelerate them. And civilizations that managed information efficiently usually outperformed those that did not. Better records meant more predictable taxation. Better taxation meant more stable governments. Better logistics meant stronger militaries. Better archives meant faster scientific progress. Even ancient warfare often became a battle between organizational systems as much as armies. The civilizations capable of coordinating resources effectively usually survived longer, but there was always a hidden fragility underneath these systems. Almost all ancient information systems depended on physical storage. Clay breaks, papyrus burns, ink fades, libraries collapse, and when records disappeared, civilizations sometimes lost enormous portions of their functional memory almost instantly. This happened repeatedly throughout history. A city burns and legal records vanish. An empire falls and tax systems collapse with it. An invading army destroys archives and suddenly nobody knows who owns land anymore. When information systems fail, societies become disoriented frighteningly fast. Because information is not just knowledge. It is continuity. Without continuity, civilization starts forgetting itself. And the larger societies became, the worse this problem got. By the late ancient world and into the medieval period, governments, religious institutions, merchants, and courts were generating mountains of paperwork. Every transaction produced records. Every law created documentation. Every trade route generated inventories. Every kingdom accumulated archives. Information was multiplying faster than human beings could comfortably manage it. And this created something history had never seen before. A bureaucracy explosion. Entire populations of scribes, clerks, archivists, accountants, and administrators emerged whose only responsibility was organizing information. Not creating it, but analyzing it. Simply keeping civilization's memory functional. Because by this point, losing information had become economically catastrophic. A missing trade record could trigger financial disputes. A lost legal decree could destabilize governance. A damaged census could break taxation systems. The problem was no longer storing information. Humanity had solved that thousands of years earlier. The problem was scale. Civilizations were producing more information than human systems could efficiently process, and buried inside that growing mountain of paper was a fatal weakness. Because paper has limits, it can be copied slowly, searched slowly, organized slowly, transported slowly, updated slowly, and worst of all, human beings still had to manage all of it manually. which meant the entire memory system of civilization was becoming increasingly fragile under its own weight. And eventually, paper would no longer be enough. For most of human history, information moved slowly because humans moved slowly. A message carried across an empire traveled at the speed of a horse. Records accumulated gradually, governments remained relatively small, and paper systems, while imperfect, were usually enough to keep civilization functioning. The Industrial Revolution arrived and shattered that balance completely. Factories multiplied production. Railroads compressed distance. Steamships accelerated global trade. Cities exploded in size. And suddenly humanity was generating information at a scale no civilization had ever experienced before. More people meant more births, more deaths, more taxes, more property records, more contracts, more legal disputes, more shipments, more inventory logs, more employee records, more insurance claims, more bank transactions. The amount of information being produced did not grow steadily. It detonated, and the old systems began breaking under the pressure. Imagine walking into a major government archive in the late 1800s. Thousands upon thousands of paper records stacked floor to ceiling. Cabinets, shelves, boxes, folders. Entire rooms dedicated to census forms alone. Rows of clerks hunched over desks, manually copying information from one sheet to another for 10 hours a day. The modern world was being built by exhausted people drowning in paperwork. And the terrifying thing was that there seemed to be no alternative, because civilization itself had become dependent on information processing. Banks needed records of loans, withdrawals, deposits, interest payments, and ownership transfers. Insurance companies needed actuarial records. Governments needed tax data. Factories needed inventory systems. Railroads needed scheduling systems. Hospitals needed patient records. Everything was becoming data, and human beings were struggling to keep up. This was especially visible in banking. Before industrialization, most financial activity happened locally. A merchant might know his customers personally. Transactions remained relatively manageable, but industrial capitalism changed finance into a massive interconnected system. Now banks handled enormous volumes of transactions every single day. Paper ledgers tracked deposits manually. Employees calculated balances by hand. Entire departments existed solely to organize records, and mistakes became terrifyingly expensive. One misplaced decimal, one lost transaction sheet, one clerical error in a major account. Small human mistakes could now ripple through enormous financial systems, and the larger these institutions grew, the more fragile their information systems became. Governments faced the same nightmare. Take the census. Counting population sounds simple until the population becomes enormous. The United States Census of 1790 counted fewer than 4 million people. By 1880, the population had exploded past 50 million. Every citizen generated data: names, addresses, occupations, family relationships, immigration status, property ownership, and every piece of information had to be collected, verified, organized, stored, and analyzed manually. The 1880 U.S. Census took nearly 8 years to fully process. 8 years, which created an absurd problem. By the time the government finished analyzing the data, the country had already changed dramatically. The information was becoming obsolete faster than humans could process it. This is one of the defining tensions of modern civilization. The faster society moves, the more important information becomes. But the more information grows, the harder it becomes to manage. And by the late 19th century, humanity was hitting a wall. Paper systems simply could not scale indefinitely. The problem was not just storage. Paper itself was physically overwhelming. Entire office buildings became giant memory warehouses. Corporations hired armies of clerks whose entire existence revolved around filing, retrieving, copying, sorting, and transporting documents from one room to another. Some government archives became so massive that locating a single document could take days. A single fire could destroy decades of records permanently. A flood could erase legal ownership histories. A filing mistake could bury information so completely it might as well not exist at all. And underneath everything sat the same uncomfortable truth humanity had been wrestling with since ancient Sumer. Human memory is unreliable. Now, even external memory systems were becoming unreliable too. The information overload was not just technical, it was psychological. By the early 1900s, modern bureaucracy had become a machine humans themselves barely understood anymore. Workers specialized so narrowly that many spent entire careers processing tiny fragments of larger information systems they could never fully see. One clerk updates census forms. Another processes tax receipts. Another organizes shipping manifests. Another copies legal records. The system grows larger. The workers become smaller, and civilization starts feeling less like a community and more like an enormous information processing organism. Writers and philosophers of the era noticed this transformation happening in real time. Cities felt faster, noisier, more complicated. Human beings were increasingly surrounded by systems they depended on but could not fully comprehend. Railroad schedules, financial ledgers, government archives, industrial logistics, information networks were becoming invisible infrastructure holding modern life together, and almost all of it still depended on paper. Paper forms, paper receipts, paper archives, paper catalogs, paper indexes. Human civilization was trying to run an industrial-scale world using medieval memory technology. Something was going to break, and the pressure kept building. Businesses demanded faster accounting. Governments demanded faster statistics. Military planners demanded faster logistics. Banks demanded faster transaction processing. Everyone wanted information processed faster than human beings could physically manage it. The old methods were no longer inefficient. They were becoming impossible. Then, in the middle of this growing crisis, one invention changed information forever. In the late 1800s, the United States government realized it had created a problem so large that human beings might not be able to solve it anymore. Not war, not famine, not political collapse. Information, specifically too much of it. Every 10 years, the United States conducted a national census. The goal sounded simple enough: count the population and gather demographic data. But by 1880, the country had transformed into an industrial giant exploding with growth. Millions of immigrants were arriving. Cities were expanding upward and outward simultaneously. Railroads connected distant states into one enormous economic machine. Every person generated information: name, age, occupation, birthplace, family relationships, property, citizenship. The census no longer meant counting people. It meant processing a mountain of data large enough to overwhelm the government itself. The 1880 census took almost 8 years to fully tabulate by hand. Think about how absurd that is. By the time officials finished analyzing the information, the country had already changed completely. The next census was approaching before the previous one had even been fully processed. Civilization was outrunning its own memory systems, and somewhere inside that growing bureaucratic nightmare was a young engineer named Herman Hollerith. Hollerith was not trying to invent the future, at least not consciously. He was trying to solve a very practical problem. How do you process enormous amounts of information faster than human clerks can? The solution was strange, elegant, and revolutionary. Punch holes into cards. That was it. A simple rectangular paper card with specific positions representing specific pieces of information. A hole punched in one location might represent male. Another location might represent female. Different patterns represented age ranges, marital status, nationality, occupation. For the first time in history, information became machine readable, not readable in the modern digital sense, but readable by a system other than a human brain. And that changed everything. Hollerith built electromechanical tabulating machines capable of processing these punched cards automatically. The metal pins passed through the holes in the cards and completed electrical circuits, allowing the machine to count and sort information mechanically. That sounds primitive now, but at the time, it felt almost magical. Data entered a machine. The machine processed it. Results emerged dramatically faster than human workers could manage manually. The speed difference was staggering. The 1890 US Census, using Hollerith's tabulating system, was completed in roughly 1 year instead of nearly a decade. 1 year, an information processing breakthrough at civilization scale. And suddenly governments, businesses, and institutions everywhere realized something profound. Machines could process information faster than people. That realization quietly altered the direction of modern civilization, because once information becomes machine processable, entirely new forms of organization become possible. Insurance companies became interested immediately. Railroads became interested. Banks became interested. Governments became obsessed. The industrial world had been suffocating under paperwork, and now, for the first time, there appeared to be a path forward. Not by reducing information, but by mechanizing its processing, and mechanization changes the psychology of scale. Before Hollerith, more information meant more clerks, more buildings, more paperwork, more delays. But machines introduced a different possibility. Maybe information systems could scale faster than human labor. Maybe civilization's growing memory problem was solvable after all. Hollerith's company eventually evolved through mergers into something called the Computing Tabulating Recording Company. Years later, that company would rename itself International Business Machines. IBM, one of the most influential technology companies in human history, emerged partly from a census crisis. Which is fitting, because databases were never really born from abstract theory. They were born from civilization becoming too complicated for human memory alone. By the early 1900s, punched cards had spread everywhere. Factories used them for inventory systems. Governments used them for population records. Banks used them for financial processing. Insurance companies used them to manage policies and risk calculations. Large organizations increasingly resembled giant information processing engines, and inside those engines sat rooms filled with machines rhythmically sorting, counting, and organizing punched cards hour after hour. The imagery of this era is strangely cinematic. Massive halls, rows of mechanical tabulators clicking endlessly, workers feeding stacks of cards into machines, the sound of civilization processing itself. And perhaps for the first time in history, machines were not merely amplifying physical labor. They were amplifying cognitive labor. That distinction matters enormously. The steam engine amplified muscle. The tabulating machine amplified information handling. Human civilization was beginning the transition from industrial power to informational power. And once that shift began, it accelerated rapidly, because the punched card introduced a dangerous and intoxicating idea. Information could be standardized. A human life could become fields on a card: age, occupation, address, income, status. Once information becomes standardized, it becomes sortable, searchable, countable, comparable, controllable. This is one of the hidden turning points of modern history. The world was slowly becoming data, not metaphorically, literally. Governments increasingly viewed populations through statistics. Corporations viewed customers through records. Institutions viewed workers through files. The modern bureaucratic state was emerging alongside machine-readable information systems, and with it came both extraordinary efficiency and extraordinary impersonality. Because machine systems do not understand people, they understand categories, fields, entries, values, data. Still, punched cards had limits. They were faster than paper systems, but they remained physical objects requiring transportation, storage, and maintenance. Machines could sort information mechanically, but they could not truly think about it. And the volume of global information kept growing relentlessly. More businesses, more records, more communication, more transactions, more complexity. Human civilization had solved one bottleneck only to discover an even larger one waiting ahead, because now the question was no longer, how do we store information? The question was becoming, how do we process information at machine speed? And the answer to that question would lead directly to computers. By the 1930s and 1940s, human civilization had reached a strange threshold. Machines could already help organize information. Punch cards could count people. Tabulators could sort records. Mechanical systems could process data faster than armies of clerks. But underneath all of it was still the same limitation that had haunted information systems for thousands of years. Everything remained physical. Physical cards, physical filing systems, physical movement. Human beings still had to carry information from one machine to another by hand. And the world was becoming too fast for that. Then war accelerated everything. It often does. World War II created logistical and mathematical problems so enormous that governments became desperate for machines capable of computation at unprecedented speed. Artillery calculations, ballistics trajectories, cryptographic analysis, supply chain coordination, radar systems. Military strategy was becoming mathematical, and mathematics at industrial scale quickly becomes impossible for human beings alone. This is the environment that produced one of the first great electronic computers in history, ENIAC. The Electronic Numerical Integrator and Computer, completed in 1945 at the University of Pennsylvania, ENIAC did not look like the future people imagine today. It was not sleek. It was not elegant. It occupied an entire room. Actually, several rooms. It weighed around 30 tons, contained roughly 18,000 vacuum tubes, consumed enormous amounts of electricity, generated intense heat. When it powered on, parts of Philadelphia reportedly experienced dimming lights. But appearances were misleading, because inside that giant machine, something extraordinary was happening. Information was no longer merely being stored mechanically. It was being processed electronically at speeds no human system could approach. ENIAC could perform thousands of calculations per second. That number sounds unimpressive today. A modern smartphone surpasses it effortlessly. But at the time, it felt almost supernatural. Problems that once required weeks of human labor could now be solved in hours, and the implications extended far beyond warfare. Because once information becomes electronic, it stops behaving like physical paper. Paper exists in one place at one time. Electronic information behaves differently. It can move, transform, replicate, process at near unimaginable speed. This was the beginning of data entering the digital world. Although the word digital itself comes from something surprisingly ancient. The Latin word digitus. Finger. Human beings originally counted using fingers, and now civilization was building electronic systems capable of counting billions of times faster than biological brains ever could. But early computers still had enormous limitations. ENIAC, for all its revolutionary power, was incredibly difficult to reprogram. Changing tasks often required physically rewiring portions of the machine itself. The machine was powerful, but inflexible. And flexibility matters enormously once information systems grow complex. The next challenge became memory. How do you store information electronically in a way that machines can retrieve efficiently? Humanity had already experimented with clay tablets, papyrus, books, punch cards. Now it needed artificial memory for electronic machines. One early solution was magnetic tape. The concept was deceptively simple. Information could be encoded magnetically onto long strips of tape and later read by machines. This transformed storage capacity dramatically. For the first time, enormous quantities of information could exist electronically rather than physically on paper. Businesses immediately recognized the potential. Governments did too. Banks especially became interested because financial systems generate extraordinary amounts of data continuously. Transactions, balances, transfers, loans, interest calculations, customer records. Paper systems were collapsing under the scale of modern finance. Magnetic storage offered something civilization desperately needed: persistent machine memory. Once organizations began storing information electronically, another transformation quietly began. Information became sequential. This matters more than it sounds. Early magnetic tape systems processed data in sequence. To access information stored in the middle of a tape, the machine often had to pass through everything before it first. Like rewinding through a movie cassette to find one scene, primitive by modern standards, but revolutionary compared to paper archives. Machines could process massive streams of information continuously without human beings manually sorting records every step of the way. This gave rise to the first true electronic data processing systems. Governments used them for census operations. Military organizations used them for logistics and intelligence. Large corporations used them for payroll systems, inventory management, and accounting. The modern information economy was beginning to emerge, and it changed the nature of institutions themselves. Companies were no longer just physical organizations. They were becoming information processing systems. Banks process financial information. Airlines process scheduling information. Governments process citizen information. Insurance companies process risk information. Modern civilization increasingly depended on organizations capable of handling vast amounts of data reliably, and computers were becoming the nervous system underneath all of it. But these early systems still felt limited, rigid, fragmented. Information existed, but organizing and retrieving it remained difficult. Different departments stored data differently. Systems rarely communicated cleanly with each other. Records duplicated constantly. Errors spread through systems quietly. The problem had evolved. Civilization was no longer struggling merely to store information. It struggled to organize electronic information coherently. And the emotional significance of this moment is easy to underestimate, because humanity was doing something profoundly strange. It was inventing artificial memory. For thousands of years, civilization relied on biological memory supported by physical records. Now memory itself was becoming electronic, detached from human minds, stored inside machines, accessible instantly, preservable indefinitely. At least in theory, and this introduced a subtle psychological shift in how humans related to knowledge itself. Information no longer felt tied to people. It felt tied to systems. A company could lose employees but retain its records. Governments could replace administrators without losing institutional memory. Organizations became increasingly immortal compared to the humans inside them. And as computing systems improved through the 1950s and 1960s, the amount of digital information exploded rapidly. Businesses digitized records. Governments digitized archives. Banks digitized transactions. The world was slowly converting reality itself into machine-readable information. But storing information electronically created a dangerous new challenge almost immediately, because once information becomes digital, duplication becomes easy, and duplication creates chaos. Different departments maintain conflicting copies of records. Updating one system does not update another. Errors multiply invisibly. Data becomes fragmented across organizations. Humanity had solved the problem of electronic storage, but storing information was not enough. Now civilization needed a way to structure digital memory itself. By the 1960s, computers were no longer experimental curiosities locked inside military laboratories. They were spreading into corporations, governments, universities, banks, insurance companies. And everywhere they went, they created the same strange problem: too much digital information. At first, organizations handled this the simplest way they could imagine: separate files, payroll records in one system, inventory records in another, customer information somewhere else, shipping records somewhere else again. Every department built its own little island of data, and for a brief moment, this seemed manageable. And the system started growing and growing and growing until companies realized they had accidentally created digital chaos because early file systems had a hidden weakness that became catastrophic at scale: data duplication. Imagine a large insurance company in 1965. A customer's name might exist in billing files, policy files, payment records, claims records, customer service records, and regional office systems simultaneously. Imagine the customer changes address. Every copy of that information must also change. Miss one file, and suddenly different parts of the company believe different realities. One department sends bills to the old address. Another sends policy updates to the new one. The claims office cannot verify identity because the records conflict. The larger the organization became, the more duplication multiplied, and duplicated information is dangerous because inconsistencies spread invisibly. This is one of the first deep truths of database design. The real enemy is not lack of information, it is disorganized information. By the mid-1960s, companies were drowning in fragmented digital records, and the systems themselves were becoming unbelievably complicated. Programmers often had to write custom code for almost every interaction with data. If one file structure changed, entire applications sometimes had to be rewritten. The business could not evolve without risking informational collapse. Modern civilization was becoming dependent on computers, but the computers themselves were becoming difficult to manage. And underneath the technical frustration sat a deeper realization. Humanity had digitized information, but it still did not fully understand how information should be organized inside machines. This is where Charles Bachman enters the story. Bachman was an engineer working at General Electric, and in many ways, he stood at the edge of a new intellectual frontier. Not computation, not hardware, data organization itself. In 1964, Bachman helped develop something called the Integrated Data Store, often considered one of the first true database management systems. And what made it revolutionary was not merely storage. It was relationships. The system allowed different pieces of information to connect to each other dynamically. Customer records could connect to orders. Orders could connect to inventory. Inventory could connect to suppliers. For the first time, data inside computers started behaving less like isolated files and more like an interconnected structure. This was a massive conceptual leap, because real life itself is relational. People connect to addresses. Addresses connect to cities. Cities connect to governments. Governments connect to laws. Reality is a network of relationships, and databases were beginning to imitate that structure. One early approach became known as the hierarchical database model. Imagine a tree. At the top sits a parent record. Below it sit child records. A company record might contain employee records beneath it. Each employee record might contain payroll records beneath that. The structure was organized, predictable, and relatively efficient. IBM became one of the major forces behind this approach. And during this era, IBM's influence over computing was enormous. The company did not merely sell machines. It shaped how organizations thought about information itself. Its systems powered governments, banks, airlines, corporations. Entire economies increasingly depended on IBM infrastructure, and hierarchical databases worked surprisingly well for certain tasks, especially when information naturally followed parent-child structures. Reality rarely stays neat for long, because real relationships are messy. An employee might work across multiple departments. A supplier might provide products to many divisions simultaneously. A customer might hold multiple accounts connected in multiple ways. The tree structure began breaking under the complexity of real-world information. So another model emerged: the network database. Instead of rigid trees, records could now connect more flexibly through networks of relationships. One piece of data could link to many others dynamically. In theory, this solved many limitations of hierarchical systems. In practice, it introduced a different nightmare: complexity. The systems became astonishingly difficult to maintain. Programmers had to manually navigate complicated pathways between records. Applications became tightly coupled to the exact structure of the data underneath them. Changing one relationship could ripple unpredictably through entire systems. Businesses increasingly found themselves trapped inside giant informational labyrinths barely anyone fully understood anymore, and this created a strange contradiction. Computers were supposed to simplify information management. Instead, organizations were becoming prisoners of their own data structures. By the late 1960s, many large corporations faced an invisible crisis. Their systems technically worked, but they were fragile, rigid, expensive, difficult to modify. The amount of digital information kept increasing faster than the systems designed to manage it, and underneath the technical frustration was a philosophical problem no one had fully solved yet. What is the best universal way to organize information? Not for one company, not for one application, for civilization scale computing itself, because every organization was inventing its own custom logic, its own structures, its own rules, its own methods of storing and retrieving information. There was no universal language for data, no clean abstraction, no elegant foundation underneath the growing complexity. And complexity scales badly. Every new application added more dependencies, more duplication, more maintenance costs, more opportunities for catastrophic failure. Companies spent enormous amounts of money simply trying to keep their information systems from collapsing under their own weight. Programmers became translators between incompatible systems. Businesses became dependent on specialists who understood ancient data architectures nobody else could navigate. And the larger institutions became, the more terrifying this problem grew, because now civilization itself was becoming digital. Banks depended on databases. Governments depended on databases. Airlines depended on databases. Military systems depended on databases. Information had become infrastructure, but the infrastructure was unstable. Humanity needed something cleaner, something universal, a system flexible enough to model almost any kind of information without collapsing into chaos. And in 1970, a mathematician working at IBM would completely change the field. In 1970, a quiet British mathematician working at IBM published a paper with a title so dry that almost nobody outside computer science remembers it today: A Relational Model of Data for Large Shared Data Banks. It does not sound revolutionary. It sounds like something designed specifically to put people to sleep, but hidden inside that paper was one of the most important ideas in the history of modern civilization. Because Edgar F. Codd was not merely proposing a better way to organize computer records. He was proposing an entirely different philosophy of information itself. And once you understand it, you start seeing the structure everywhere. Before Codd, databases were tangled machines. Hierarchical systems forced information into rigid trees. Network databases became sprawling webs of complicated connections. Programmers had to think constantly about how information physically moved through the system. The databases worked, but they felt fragile, like giant mechanical cities barely holding themselves together. Codd looked at this chaos and asked a deceptively simple question. What if data organization could be abstract? Not tied to physical pathways, not trapped inside hard-coded structures. What if information could simply exist as relationships? That idea changed everything. To understand why, imagine a spreadsheet, not even a modern one, just a simple table. Rows, columns, clean structure. One row might represent a customer. The columns describe attributes about that customer: name, address, phone number, account balance. Every customer follows the same structure. Simple, predictable, organized. This does not sound revolutionary now because relational databases became so successful that they reshaped how modern people think about information itself. But at the time, this was a conceptual earthquake. Because Codd realized something profound. Most information in the real world can be represented through relationships between structured tables. Customers place orders. Orders contain products. Products belong to suppliers. Employees belong to departments. Students enroll in courses. Bank accounts belong to customers. Reality itself is relational, and suddenly, databases no longer needed to mirror complicated machine structures. They could mirror logic instead. This was the breakthrough. God separated how information is stored physically from how humans think about information conceptually. That sounds abstract, but it solved an enormous problem. Before relational databases, programmers often had to manually navigate data structures step by step. The machine cared deeply about where information physically existed and how to reach it. Relational systems changed the question entirely. Instead of telling the machine how to retrieve data, humans could simply describe what they wanted. Find all customers in Chicago. Retrieve all orders placed this month. Calculate total sales by region. The database itself figured out how to execute the request efficiently. This sounds normal now because modern computing inherited this philosophy completely, but in 1970 it felt almost magical. The machine was no longer just storing information. It was reasoning about structure. And underneath this system sat a surprisingly elegant idea. Tables could connect to each other through shared values. A customer table contains customer IDs. An orders table also contains customer IDs. A shared field creates a relationship. Now the system understands which orders belong to which customer without duplicating all customer information repeatedly. This solved one of the great nightmares of early computing: redundancy. No more storing the same information everywhere. No more massive inconsistencies spreading through organizations. Update the customer information once. Every connected system sees the update automatically. Chaos started becoming structure, and this is where the emotional significance of relational databases becomes easy to underestimate. Because this was not just a technical breakthrough, it was civilization discovering a more intelligent way to organize memory. For thousands of years, humans stored information physically: clay tablets, scrolls, books, paper archives, file systems. But relational databases introduced something fundamentally different. Information became logical, dynamic, interconnected, searchable at scale. Modern civilization quietly reorganized itself around this idea. Banks adopted relational systems because financial data depends heavily on consistency and relationships. Airlines adopted them because reservations, schedules, and passenger records form interconnected networks. Governments adopted them because census systems, taxation systems, and legal records require structured integrity. Businesses adopted them because managing customers, inventory, payroll, and transactions became dramatically simpler. Once relational databases spread, modern software development exploded because programmers no longer needed to reinvent information systems constantly. A universal model finally existed, but Codd's ideas initially faced resistance. Ironically, even IBM hesitated. Many engineers believed relational systems would be too inefficient compared to existing database architectures. After all, abstraction often introduces overhead, and early computers were painfully limited by modern standards. Storage was expensive. Memory was tiny. Processing power was scarce. Some critics viewed relational databases as mathematically elegant but impractical. Then reality intervened because complexity was becoming the dominant problem of computing, and complexity destroys systems over time. The larger organizations became, the more valuable simplicity became. Relational databases simplified development dramatically. They simplified maintenance. They simplified scalability. Most importantly, they simplified human understanding. And human understanding is often the real bottleneck in technological systems. A brilliant system nobody can understand eventually becomes unusable. Relational databases succeeded partly because they align naturally with how human beings already think. Tables, categories, relationships. The structure feels intuitive because reality itself behaves relationally. And to interact with these systems, another revolutionary idea emerged: SQL, structured query language. SQL became the language humans used to communicate with relational databases, and SQL introduced one of the most important shifts in computing history: declarative logic. Instead of programming every step manually, users simply declared what they wanted. Select customers from Chicago. Sum all sales from last month. Find all unpaid invoices. The database engine handled the complexity underneath automatically. This was enormously powerful because it democratized information access. You no longer needed deep knowledge of physical storage systems to retrieve useful information. The abstraction layer handled it for you. And abstraction is one of the defining superpowers of computer science. Hide complexity underneath simpler interfaces. Again and again and again, the transistor hides quantum physics. Programming languages hide machine code. Operating systems hide hardware complexity, and relational databases hide the chaos of information storage. Once this model spread through the 1970s and 1980s, it became the invisible foundation of modern digital civilization. Banks, hospitals, governments, retail companies, airlines, universities, almost everything storing structured information eventually adopted relational principles in some form. The reason relational databases won was not merely technical superiority. It was flexibility. Reality changes constantly. Businesses evolve, organizations grow. Information structures shift over time. Rigid systems break under that pressure. Relational systems adapted. New tables could be added. Relationships could evolve. Queries could become more sophisticated. Models scaled intellectually as civilization became more complicated, which is why Codd's work feels strangely philosophical in retrospect. He transformed information from static records into dynamic relationships, and that mirrors something true about reality itself. Nothing exists entirely alone. Everything connects people, cities, economies, governments, ideas. The modern world is not merely a collection of isolated facts. It is a gigantic relational system, and relational databases became humanity's first truly successful attempt to model that complexity digitally. This was the moment databases stopped being storage systems and became something larger: a universal architecture for organizing civilization's memory. But success creates new problems, because once databases became powerful enough to organize massive amounts of information reliably, the world started generating even more information than anyone had imagined possible. And soon, databases would become the hidden engine underneath the internet itself. By the 1980s, databases had quietly escaped the world of computer scientists and entered ordinary life. Most people just did not realize it yet, because databases are almost invisible when they work correctly. You do not see them. You experience the systems built on top of them. The ATM works, the airline ticket appears, the inventory updates, the hotel reservation confirms, the bank balance changes. Underneath all of it, databases are constantly answering questions. Who is this person? What do they own? What changed? What exists? What happened 5 seconds ago? Modern civilization increasingly became a conversation between human beings and giant invisible memory systems. And the language powering much of that conversation was SQL, structured query language. At first glance, SQL looks surprisingly ordinary, almost conversational. Select name from customers. Find all flights going to Chicago. Show all transactions from yesterday. Underneath the technical syntax sits a remarkably human idea: ask questions about information. That is what SQL really is, a way of interrogating memory. And what made SQL revolutionary was not merely that it retrieved information. It allowed human beings to interact with enormous data systems without needing to understand how the machine physically stored everything underneath. This mattered enormously, because by now databases were becoming massive: millions of records, then tens of millions, then hundreds of millions. No human being could manually navigate systems at that scale efficiently, so relational databases relied on another crucial invention: indexes. An index in a database works a lot like the index in a book. Imagine trying to find one sentence inside a 1,000-page textbook without an index. You would need to scan page after page manually. Painfully slow. Now imagine the book already contains a structured map pointing directly to important topics. Instant retrieval. Databases face the same problem at much larger scale. Without indexes, searching enormous tables would become unbearably slow as systems grew. So databases built internal maps, allowing machines to locate information rapidly without scanning everything sequentially. This sounds technical, but emotionally, it is civilization inventing faster memory retrieval, not just remembering information, finding it instantly. And speed changes human behavior dramatically. When retrieving information becomes fast enough, entire industries reorganize around the assumption of immediate access. Banking is one of the clearest examples. Imagine checking your bank account before databases existed. Paper records, manual verification, human clerks physically locating transaction histories. Now imagine millions of people trying to access financial information simultaneously in real time. Impossible without databases. Modern banking systems rely on transactions, one of the most important ideas in database history. A transaction is essentially a promise. Either all parts of an operation happen successfully, or none of them happen at all. This matters because financial systems cannot tolerate partial reality. Suppose you transfer $500 from one bank account to another. If the first account loses the money, but the second account never receives it because of a system failure, the entire financial system becomes untrustworthy. Databases solve this through transactional integrity. The operation either completes fully or reverses safely. This reliability is one of the hidden foundations of modern civilization. Most people trust digital systems without thinking about why. But trust emerges from consistency. Your balance updates correctly. Your payment history persists. Your records survive failures. Databases quietly created the conditions for large-scale digital trust. Airline systems pushed these ideas even further. Airlines generate astonishingly complicated information problems. Flights connect across continents. Seats change constantly. Passengers cancel. Weather disrupts schedules. Crew assignments shift. Pricing updates dynamically. And all of this information must remain synchronized globally in real time. When you reserve a seat on a flight, the system must instantly know whether someone else already purchased that seat seconds earlier somewhere else in the world. Without databases coordinating this information continuously, modern air travel becomes chaos almost immediately. This revealed something increasingly important about databases. They were no longer passive storage systems. They had become active coordination systems for civilization itself. Banks coordinate money, airlines coordinate movement, governments coordinate populations, corporations coordinate logistics. Every large modern institution increasingly depended on databases to maintain coherent reality internally. Then came the internet, and everything accelerated again. The early internet of the 1980s and early 1990s was relatively small, academic, technical, decentralized. But once the World Wide Web emerged, suddenly millions of ordinary people began interacting with digital systems daily. Websites stopped being static documents. They became dynamic systems generating information in real time. And behind almost every dynamic website sat a database. The user logs in. The database verifies identity. A shopping cart updates. The database tracks products. A forum post appears. The database stores conversations. A search query runs. The database retrieves results. The modern web became unimaginable without databases, and e-commerce pushed this transformation to another level entirely because online shopping requires an astonishing amount of coordinated information. Products, prices, users, payments, shipping addresses, inventory, order histories, recommendations. Every click generates data. Every purchase modifies data. Every customer interaction depends on databases remaining accurate continuously. Companies like Amazon were not merely retail businesses. They were giant information systems wrapped around logistics networks. And as internet traffic exploded through the late 1990s and early 2000s, databases quietly became some of the most important infrastructure on Earth. Not roads, not ports, not factories. Databases. Invisible systems storing the memory of modern civilization. And most people never noticed because successful infrastructure disappears psychologically. You only think about electricity when the power fails. You only think about databases when something breaks, when your payment disappears, when your account stops working. When reservation systems collapse, when records vanish, but underneath daily life, databases were coordinating reality at extraordinary scale. Every social media profile, every hospital record, every tax payment, every online purchase, every streaming recommendation, every GPS route, every message, every search. The digital world increasingly became a gigantic network of interconnected databases constantly updating each other. Something subtle happened to human psychology during this period. People began expecting memory to be permanent, searchable, instant. You no longer needed to remember phone numbers because systems remembered for you. You no longer needed physical photo albums because digital archives persisted automatically. Human beings started outsourcing memory itself to databases at civilization scale. And once that process began, there was no going back. Success created a dangerous new problem because the internet was generating more information than traditional databases had ever been designed to handle. Millions of users became billions. Data stopped growing linearly, exploded exponentially, and the systems that once seemed infinitely powerful suddenly started approaching their limits. At some point in the early 2000s, humanity crossed an invisible line. For thousands of years, the problem had been preserving information. Now the problem became surviving it, because the internet did something no previous technology had ever done. It turned billions of human beings into continuous data generators. Every email, every search, every message, every uploaded photo, every GPS location, every online purchase, every click, every second. Civilization was no longer merely storing information occasionally. It was producing information constantly at a planetary scale. And suddenly, even the most sophisticated database systems in the world began feeling small. Google was one of the first companies to encounter this reality directly. First, the web itself seemed manageable. A growing collection of websites connected by hyperlinks. But growth on the internet does not behave normally. It compounds exponentially. Millions of pages became tens of millions, then hundreds of millions, then billions. And Google faced a terrifying question. How do you organize humanity's information when the information never stops growing? This was not merely a search problem. It was a database problem at civilization scale. Because search engines are fundamentally giant retrieval systems. They crawl the web, store information, index relationships, rank relevance, retrieve results instantly. Doing this for billions of pages required an entirely new way of thinking about data infrastructure. Traditional databases had largely assumed systems would operate on single machines or tightly controlled servers. Google realized that future scale information systems would require thousands of machines working together simultaneously. This changed everything because once data becomes large enough, no single computer can hold all of it anymore. Information must fragment across enormous distributed systems. Pieces of reality stored in different physical locations while still behaving like one unified system. This sounds abstract until you imagine the scale involved. Google indexes hundreds of billions of web pages, processes trillions of searches every year, stores unimaginable amounts of information across massive global infrastructure. The scale becomes difficult for the human brain to visualize properly. A single modern data center can contain hundreds of thousands of servers, miles of cables, industrial cooling systems, backup power infrastructure, buildings consuming as much electricity as small cities, and inside them, machines constantly storing, copying, organizing, and retrieving humanity's digital memory. The internet stopped being virtual a long time ago. It became physical infrastructure. Warehouses full of machines remembering civilization on our behalf. Social media arrived and made the situation even more extreme. Google primarily organized information humans created intentionally. Facebook organized human relationships themselves, and relationships generate extraordinary amounts of data, friend connections, messages, photos, likes, comments, location histories, interactions, social graphs. A social graph is essentially a gigantic map of human relationships. Who knows whom? Who interacts with whom? Who influences whom? And at Facebook scale, this became one of the largest relational systems ever constructed. Billions of people, trillions of connections, constant updates happening every second. Traditional databases were never designed for anything remotely close to this scale because the internet was not merely growing larger, it was becoming alive, continuous, real time. Every second, millions of users generated new information simultaneously. And unlike older systems, modern platforms could not simply archive data quietly in the background. They needed instant responsiveness. Messages appear immediately. Notifications update instantly. Feeds refresh continuously. The expectation of real-time digital reality became normal astonishingly quickly. Then YouTube introduced another layer of complexity: recommendations. At first glance, recommendation systems seem simple. Show viewers videos they might enjoy, but underneath that innocent feature sits one of the largest data processing challenges ever attempted, because recommendations require understanding behavior itself. What do people watch? For how long? What do they skip? What do similar users enjoy? What patterns emerge across billions of viewing sessions? YouTube is not just storing videos, it is storing behavioral information about human attention, and then using that information to predict future behavior in real time. This required databases to evolve beyond static storage systems, and how they needed to support machine learning, analytics, personalization, and predictive modeling at unimaginable scale. The phrase big data emerged partly because traditional language stopped capturing the magnitude of what was happening. Humanity had entered the age of informational abundance. Actually, informational excess. Every minute, hundreds of hours of video uploaded, millions of messages, sent millions of searches, performed millions of financial transactions, processed millions of photos shared. The numbers quickly become absurd. And what is fascinating is that most of this data is mundane, tiny fragments of ordinary life. A search query, a location ping, a food order, a photo upload. Collectively, these fragments form the largest information system humanity had ever created. A digital mirror of civilization itself. And underneath it all sat databases straining under impossible pressure, because traditional relational systems excelled at consistency and structure. But internet-scale systems introduced new priorities: speed, scalability, fault tolerance, global distribution. The systems now needed to survive hardware failures continuously, because at large enough scale, failures become normal. Not possible. Inevitable. If a company operates 10 servers, failures are occasional. If it operates hundreds of thousands, something breaks constantly. Drives fail. Machines overheat. Network connections collapse. Power systems malfunction. So internet companies design distributed systems capable of surviving permanent instability. Data replicated across multiple servers, across multiple buildings, across multiple continents. One machine dies. The system continues. An entire data center fails. Traffic reroutes elsewhere. Modern databases increasingly resembled living organisms adapting dynamically to damage. And the emotional reality underneath all of this is strange. Human civilization accidentally built a planetary nervous system. Billions of people continuously generating information. Massive infrastructures processing memory collectively. Algorithms routing attention. Databases preserving identity, communication, commerce, relationships, entertainment, and knowledge simultaneously. Most people think of the internet as websites and apps. But underneath the interfaces sits something much larger, a gigantic machine for storing and processing human activity itself. And as this machine grew, another uncomfortable realization emerged. Traditional database architectures were beginning to fail under the scale of the modern internet. Relational systems remained incredibly powerful, but they struggled with the chaotic, rapidly changing, globally distributed nature of internet-scale data. The systems that once organized banks and airlines beautifully were now confronting billions of simultaneous users, endless streams of unstructured information, and real-time global interaction. The world had changed again. Information was no longer merely structured records stored carefully in tables. It had become fast, messy, decentralized, and effectively infinite. And traditional databases were starting to crack. For decades, relational databases had been the kings of digital information. Banks trusted them. Governments trusted them. Airlines trusted them. Entire industries were built on the assumption that structured tables, strict consistency, and transactional reliability were the correct way to organize data. For a long time, they were. But the internet changed the rules faster than traditional databases could adapt, because internet-scale systems introduced a problem older database architectures were never designed to solve. Global simultaneity, billions of people connected continuously. Millions of updates happening every second, data flowing across continents in real time, and suddenly the priorities of computing started shifting. In the old world, consistency mattered above almost everything else. A bank transaction must be correct. An airline reservation must not duplicate seats. A payroll system cannot randomly invent salaries. But social media feeds, recommendation systems, massive web applications, these systems valued something else too. Speed, availability, scale. And sometimes those priorities collided violently with traditional database rules. Imagine a social media platform with billions of users spread across the planet. Someone uploads a photo in Tokyo. A friend in New York refreshes their feed instantly. Another user comments from London. A recommendation algorithm updates in California. All of this happens within seconds. Now imagine trying to guarantee perfect consistency across every server in the world before allowing any user to proceed. The system becomes painfully slow. Modern internet companies realize something uncomfortable. At sufficient scale, perfect consistency becomes expensive. Sometimes impossibly expensive, and this realization triggered one of the biggest philosophical shifts in database history, the rise of NoSQL. The phrase itself was slightly misleading. NoSQL did not literally mean abandoning SQL entirely. It meant questioning the assumption that relational databases should dominate every kind of problem. Because internet data had become strange, messy, unstructured, rapidly changing. Traditional tables worked beautifully for predictable systems like banking records. But what about social media posts, chat messages, real-time analytics, massive recommendation systems, user activity streams? The web increasingly generated data that did not fit neatly into rigid relational structures. MongoDB became one of the most influential examples of this new philosophy. Instead of forcing all information into strict tables with predefined columns, MongoDB used flexible document structures. Different records could contain different fields dynamically. This sounds small, but conceptually, it was enormous. The database no longer demanded that reality fit perfectly into rigid schemas. Reality could become messier, more organic, more adaptable, and adaptability mattered because internet companies were evolving constantly. Features changed weekly. User behavior shifted rapidly. Applications scaled unpredictably. Rigid systems became liabilities. Then came Cassandra, originally developed at Facebook. Cassandra approached databases from a completely different angle. Survival at planetary scale. The system was designed to run across enormous distributed infrastructures without collapsing if parts of the network failed. This mattered because large-scale internet systems learned something brutal very quickly. Failure is inevitable, not hypothetical, not occasional, constant. At enough scale, servers are always breaking somewhere. Hard drives fail. Network links fail. Power systems fail. Entire data centers occasionally fail. Traditional database systems often assumed stable environments. Internet-scale companies no longer had that luxury, so databases evolved into distributed organisms capable of surviving continuous damage. Data replicated automatically across multiple machines, sometimes across multiple continents. One server disappears. The system continues. An entire region goes offline. Traffic reroutes elsewhere. Modern databases increasingly resembled biological systems more than traditional software. Resilient, adaptive, decentralized. Then there was Redis, fast enough to feel almost instantaneous. Redis specialized in storing information directly in memory rather than slower disk storage, allowing applications to retrieve data at extraordinary speed. Because by now, user expectations had changed dramatically. People no longer tolerated waiting. Websites needed to feel immediate. Apps needed to refresh instantly. The modern internet became psychologically addicted to speed. Milliseconds started mattering economically. A slightly slower website could lose millions of users. A delay in recommendation systems could reduce engagement dramatically. The database philosophy shifted from, can we store information correctly? To, can we retrieve information instantly at global scale? And underneath all these changes sat another transformation quietly reshaping computing itself, the cloud. Before cloud computing, companies usually maintained their own physical servers, huge expensive infrastructures requiring maintenance, cooling, power systems, networking, security, backups. Scaling meant buying more hardware manually. Expensive, rigid. Then Amazon introduced AWS, Amazon Web Services, and something profound changed. Computing infrastructure itself became rentable, on demand, elastic. A startup no longer needed giant server rooms. It could rent computational resources dynamically from cloud providers. Need more storage? Scale instantly. Traffic spikes unexpectedly? Add more servers automatically. This fundamentally changed database architecture because now systems could scale fluidly across distributed cloud infrastructure instead of remaining tied to specific physical machines. Databases became increasingly abstract, less tied to hardware, more tied to networks. And this is where one of the most important ideas in distributed computing emerges, the CAP theorem. It sounds technical, but emotionally, it is about compromise. The theorem essentially argues that distributed systems cannot perfectly guarantee all three of these simultaneously: consistency, availability, and partition tolerance at large scale. Something must give. Either systems prioritize perfect consistency, or they prioritize availability and resilience. This became one of the defining tensions of the modern internet: speed versus certainty, responsiveness versus synchronization. Should users always see the latest perfectly synchronized information, or should the system remain available even if small inconsistencies temporarily exist? Different companies answered differently depending on their needs. Banks leaned heavily toward consistency. Social platforms leaned more toward availability and scale. And this philosophical shift transformed database design permanently. The old dream of one perfect universal database system started dissolving. Instead, modern computing embraced specialization. Different problems required different database philosophies. Relational databases still dominated structured transactional systems. NoSQL systems excelled at flexibility and scale. Distributed systems optimized for resilience. In-memory systems optimized for speed. The database world fragmented into ecosystems rather than kingdoms. And underneath all of this complexity sat a strange, emotional reality. Human civilization was now producing information faster than any centralized structure could comfortably control. The internet had become too large, too dynamic, too alive, and databases were evolving from static archives into global adaptive systems trying to keep up with human behavior in real time. But another transformation was already beginning quietly in the background, because databases were no longer just storing information about the world. They were beginning to understand patterns inside it. For most of history, databases answered simple questions. Who owns this land? How much money is in this account? Which customer placed this order? The systems were powerful, but fundamentally literal. Exact matches, exact retrieval. Human beings asked precise questions, and databases returned precise answers. But human thought rarely works that way. Memory itself is fuzzy, associative, contextual. You might not remember the exact title of a song, but you remember how it felt. You might not remember someone's exact words, but you remember the meaning. Human intelligence depends heavily on similarity, patterns, and context rather than strict exact matching. And eventually, databases began evolving in that direction too. This is where the story becomes strange again, because databases are no longer merely storing information. They are starting to understand relationships inside information itself. The modern AI revolution depends partly on a concept called embeddings, and embeddings sound abstract until you realize what they really are. They are attempts to convert meaning into mathematics. Imagine asking a traditional database, find documents containing the exact word dog. Simple. Literal. Now imagine asking, find documents emotionally similar to this conversation. That is dramatically harder, because similarity is not exact. Meaning is not binary. To solve this, AI systems convert words, images, videos, songs, and even human behavior into numerical representations called vectors. A vector is essentially a list of numbers representing characteristics and relationships. Words with similar meanings end up mathematically close together. Concepts related emotionally or contextually cluster near each other inside enormous multidimensional spaces. In these systems, king sits closer to queen than to banana. Sadness clusters near grief, loneliness, sorrow. The machine no longer stores only information. It stores relationships between meanings. This is one of the most important shifts in database history. Traditional databases stored facts. Modern AI systems increasingly store semantic relationships. Meaning itself becomes searchable. And once that happened, a completely new kind of database emerged. Vector databases. Unlike traditional relational systems built around rows and columns, vector databases specialize in storing and searching embeddings efficiently. Instead of asking, find exact matches, they ask, find things most similar. This sounds subtle. It is not. It changes how humans interact with machines fundamentally, because suddenly search stops feeling mechanical. It starts feeling intuitive. Semantic search is one of the clearest examples. Old search engines largely depended on keywords. Type specific words. Receive matching pages. Modern AI-powered systems increasingly understand intent. It can describe an idea imperfectly and still retrieve relevant information, because the system understands conceptual similarity rather than literal wording alone. This is much closer to how human memory actually functions. Human beings rarely retrieve information through exact indexing. We retrieve through association. Patterns, meaning, emotion, and databases are slowly evolving in that direction. This transformation powers much of modern AI. Recommendation systems no longer simply categorize users crudely. They model patterns of behavior mathematically. Spotify predicts music preferences. Netflix predicts viewing habits. TikTok predicts attention. YouTube predicts curiosity. Every interaction becomes training data. Every click updates massive behavioral models in real time. And underneath these systems sit databases constantly processing not only what humans do, but what humans are likely to do next. That predictive layer is new. Historically, databases remembered the past. Modern AI systems increasingly attempt to anticipate the future. Nowhere is this more visible than large language models. Systems like ChatGPT operate partly through gigantic informational architectures trained on enormous amounts of human-generated text. But increasingly, these systems are also integrating memory itself, conversation history, preferences, context retention, personalization. The machine starts remembering interactions over time, not perfectly, not consciously, but functionally. And psychologically, this changes how humans relate to software. Applications stop feeling like tools. They begin feeling like entities maintaining continuity across interactions. The line between database and intelligence starts blurring. This is emotionally significant because memory has always been deeply tied to identity. Humans define themselves partly through remembered experience. Civilizations define themselves through preserved knowledge. Now, machines are developing increasingly persistent forms of contextual memory too. Not human memory, something stranger. Machine memory capable of operating at planetary scale. And the scale here becomes difficult to fully comprehend. Modern AI systems train on trillions of words, billions of images, massive behavioral datasets generated by billions of humans interacting continuously with digital systems. Human civilization has effectively become both the user and the training material simultaneously. The internet evolved from a communication network into a giant cognitive archive, a memory system for the species itself. And databases sit underneath all of it, quietly evolving from filing cabinets to semantic engines, predictive infrastructures shaping human attention in real time. This creates strange philosophical questions because recommendation systems increasingly influence culture itself. What people watch, what people buy, what people believe, what people notice. Databases are no longer passive storage systems hidden behind applications. They are becoming active participants in human decision-making, and the systems themselves are becoming more personalized constantly. Open your social media feed. Your version differs from everyone else's. Your recommendations differ. Your search results differ. Your advertisements differ. Modern databases increasingly generate individualized realities tailored dynamically to each user at internet scale. In real time, this level of personalization would have seemed almost supernatural only a few decades ago, and yet humanity adapted to it almost immediately, which may be the strangest part of technological change. The impossible becomes ordinary astonishingly fast, but underneath the convenience sits something deeper. Human civilization is entering a new relationship with memory itself. For thousands of years, memory was biological, then physical, then digital. It is becoming predictive, semantic, contextual, and increasingly intelligent. Databases are no longer simply answering questions. They are beginning to interpret intent, recognize patterns, generate responses, assist thought itself. Whether these systems eventually become something resembling true intelligence remains unclear. But one thing is already obvious. We are entering a new era. An era where the memory systems humanity built are starting to behave less like archives and more like minds. Thousands of years ago, somewhere in ancient Mesopotamia, a merchant pressed markings into wet clay because he was afraid of forgetting. That was the beginning. Not silicon, not servers, not artificial intelligence. Fear of forgetting. And in a strange way, the entire history of databases is just humanity repeatedly building larger and larger systems to compensate for the limits of human memory. First clay tablets, then papyrus archives, then libraries, then punch cards, then magnetic tape, then relational databases and cloud infrastructure stretching across continents, and now systems capable of storing and interpreting meaning itself. The technology kept changing, but the underlying human problem remained astonishingly constant. Memory is fragile. Civilization depends on overcoming that fragility, because civilizations are not really made from buildings or roads or governments. Those things matter. But underneath all of them sits preserved information. Laws survive because they are recorded. Science advances because discoveries are remembered. Economies function because transactions persist. History exists because someone stored it long enough for the future to inherit it. Without memory, civilization resets continuously. This is one of the strangest truths about humanity. Individual humans forget constantly, yet collectively, the species remembers across centuries. A mathematician dies, but the theorem survives. An empire collapses, but fragments of its records persist. A scientist publishes an idea, and hundreds of years later, someone else builds upon it. Databases are part of that continuity, not just modern databases, all systems of preserved information. In many ways, civilization itself is a memory machine, and the scale of that machine has become almost impossible to comprehend now. Every photograph uploaded, every message sent, every search query, every purchase, every article, every location ping. Humanity is producing a digital reflection of itself continuously, a gigantic externalized memory system spread across the planet, and increasingly parts of our identities live inside those systems. Bank accounts, medical histories, photos, conversations, relationships, preferences, professional records. Modern identity is partially database identity, a strange hybrid between biological memory and digital persistence. And unlike human memory, digital memory often does not fade naturally. The internet remembers things humans might prefer forgotten. Embarrassing posts, old photographs, past opinions, fragments of identity preserved indefinitely across distributed systems. For most of history, forgetting happened automatically. Now permanence is becoming the default. That changes how societies behave, how people present themselves, how reputations evolve, how history gets written, because once information becomes permanent and searchable at global scale, the relationship between past and present changes completely, and artificial intelligence is pushing that transformation even further. For most of history, databases simply stored information passively. Now AI systems increasingly interact with information dynamically, summarizing it, interpreting it, connecting it, generating new outputs from it. Human knowledge is no longer sitting quietly in archives waiting for retrieval. It is becoming computationally active. And this creates a strange possibility. Human civilization may be constructing something like a collective external intelligence, not conscious necessarily, not alive in the human sense, but increasingly capable of processing, connecting, retrieving knowledge at scales no biological civilization could achieve unaided. The ancient merchant counting grain could never have imagined this, could never have imagined billions of humans connected through invisible global systems storing enormous portions of civilization's memory electronically, could never have imagined machines capable of retrieving information instantly from across the planet, could never have imagined databases that understand meaning rather than just records. And yet, underneath all the complexity, the emotional core of the story barely changed at all. Human beings needed help remembering. That is really what databases are, memory prosthetics for civilization. Ways to preserve knowledge beyond the limits of individual minds. Ways to coordinate reality across enormous groups of strangers. Ways to prevent information from disappearing into time. And every era believed its memory systems were advanced. The clay tablet felt advanced once. The archive felt advanced once. The library felt advanced once. The punch card felt advanced once. Our modern systems feel permanent and inevitable too. But history suggests something humbling. Every information system eventually looks primitive to the future, which means the systems we consider unimaginably sophisticated today may someday appear as transitional technologies in a much longer story humanity has barely begun, because the gap that created databases still exists. Human curiosity grows faster than human memory. It always has. And somewhere in that gap between what humanity wants to remember and what it can remember alone, the future is still being built.